Well, welcome back, folks. It's now 7 o'clock. I appreciate you all making it in after the power outages many of you might have had. That can really mess up the day. But before we start today, we're discussing some of the homework problems, also questions on conditional convergence. But other questions folks would like to discuss before we start today's work? I guess I have one question myself then. Would it be helpful to do another problem from section 11.8 on finding the radius and interval of convergence? How do you folks feel about that? Okay, let's start with 11.8. Then we're going to dive into 11.9, representation of functions using power series. 11.9 is a longer section, and that's the reason just 2 sections on the homework, and the assignment 10 is now fully posted. So we'll do the section 11.9 partially today, and we'll finish it on Thursday. And Thursday we'll start section 11.10, the final section before the exam, and maybe a couple more announcements. If we go to the next week on the Moodle website, then there is one new document. It is the sample exam 3. So this document looks about like this when you open it. It has some notes on problems that won't be on the exam, like this one, which was never on the homework. And if you go to the very bottom, there's going to be solutions to all these problems. So it's just a section by section list of problems like we've seen before. And when we get a little bit closer sometime during this week, hopefully before the weekend, I'll post the exam that I gave last semester. So it'll have not only a set of all the problems, the scope of what could be asked, but also get a feel for what a real exam would look like. But essentially, it's just going to be a repeat of what we did for exam 1, exam 2, with different sections. And 11.10, 11.9 are the only 2 sections we haven't covered yet. So that brings us back to, let's do a review problem 11.8, and then see what is in store for us in 11.9. Any questions then before we start? Okay, so first, let's find the radius and interval of convergence of a new series. Instructions will say just that, find the radius and interval of convergence of, and we'll start with a power series that goes about like this. Let's see here. 1 minus a half times x minus 2 plus a fourth times x minus 2 squared minus an eighth times x minus 2 cubed plus, and then dot, dot, dot to say, and so on. So that is our power series that we'd like to find the interval and radius of convergence. It's kind of a nasty problem, and it's this type of problem that we started class on Monday with, where we have some kind of series where the nth formula, the formula for the nth term hasn't been given. So that's where we'll start. We have to first figure out what this is equal to as a sum as n goes from 0 to infinity of a sub n. So a sub n is going to be the generic nth term of this entire series or power series. But actually coming up with a sub n is a little bit faster in this context versus what we did on the start of Monday, because of the x minus 2 portion. For dealing with a power series always has this format. As n goes from 0 to infinity, we'll have a c sub n, which is going to be the nth coefficient, times x minus the center is 2, to the power of n. So that's what our power series really looks like. A sub n is equal to all of this. And we have to find a formula for the nth term, or the nth coefficient, c sub n. So that does reduce the work by a good amount. We can say, for example, when we look at this, the first coefficient, which is c sub 0, was a 1. Then c sub 1 is negative 1/2. C sub 2 is positive 1/4. C sub 3 is negative 1/8. And it'd be really nice to have a formula for c sub n, so we can plug it in way over there for our formula for the power series. But any questions so far with what we've got? Okay, so now we need a formula for c sub n, where we're really just ignoring the x minus 2, x minus 2 squared, and so on. So we're just trying to get this pattern to work out. It's going to be something to a power. And notice already this is off to a good start, because if I put in 0, then something to a power of 0 is going to give me a 1. And in this class, we do take the convention, let me put this here, by convention, whenever this happens, and it does happen, we'll use 0 to the power of 0 as a 1 in this class only. Ordinarily, that's undefined, but that just helps us work through the power series formula when we start at 0 without having to make an exception every single time on our formulas. So there is halves going on here, so I'd probably go like this. C sub n should be a half to the power of n. So if we plug in 0, a half to the power of 0 does give us 1, so we're on the right track. And I picked out a half because that's the very next term. So c sub 1 would be a half to the power of 1, but it's supposed to be negative. So we can fix that by just throwing in a negative sign as our next step. How do you folks feel about it? Does it look like it's about right? Let's do a quick eyeball check to see if we're happy with it. So if you plug in 0 to this sequence, we get negative 1/2 to the power of 0, which is a 1. So I'm happy with that. If we plug in 1, any base to the power of 1 is itself, so we get negative 1/2. So it seems about right. Let's see if it can get C2 and C3. If it matches here to here, I would say that's very strong numerical evidence. We've got the right pattern. So at C sub 2, we have 2 there. We're squaring negative 1/2. That's definitely a 4th. And if we cube negative 1/2, that would definitely be negative 1/8. So it looks like the right formula. How do you folks feel about that so far? Any questions to that step? Okay, so we started with a power series written in its expanded form. That always takes a lot of work. To combine it to this thing, this is the power series with the nth term defined to be a sub n. But all power series has this as a format, x minus 2 to a power n times the coefficient c sub n. And by the work that we've done down over there, the power series is now the summation from 0 to infinity of c sub n, which is negative 1 to the power of n. And if we'd like, we could break that up as negative 1 to the n, x minus 2 to the power of n, divided by, let's make that be 2 to the n. So that's our entire power series. Finally, we can begin the problem of finding its radius and interval of convergence. Any questions so far to build the power series? Okay, then in order to find the radius and interval of convergence, what we're doing in principle is we're imagining x varies. And we want to determine for what values of x will this series converge and for what values of x will the series diverge. And what was the number one test to get at that we've been using? Yeah, if we're dealing with a power series, then the ratio test is almost always going to be the best way to go. So let's start off by ratio test. Ratio test gives convergence when the following limit is less than 1. And that limit would be the limit as n goes to infinity of a sub n plus 1 divided by a sub n. Now when we look at a sub n, we mean the total series, including the power portion, x minus 2 to the power n, whereas c sub n just refers to the coefficients. So that's really kind of nasty. When we're dealing with power series, we have two series, a sub n, c sub n, and then a third series, which is the sequence of partial sums, or excuse me, sequences. We have 3 sequences altogether. But now this will be the limit as n goes to infinity of the absolute value. Going to the far right there, we'll take negative 1 to the power n plus 1. But because that is a value that's going to be wiped out by the absolute value, if you skipped that, that would probably be okay for this work. But we shouldn't skip x minus 2 to the power n plus 1. All of this is divided by 2 to the power of n plus 1. So this is the a n plus 1 term that we're going to divide by a sub n, which is multiplying by the reciprocal of all that. So that's a sub n, and we have this divided by a sub n gives us 2 to the power of n, divided by, oh, forgot the negative 1 to the power of n as well. I guess we could put that wherever we'd like. Let's keep it in the denominator, just to keep the pattern a little bit more consistent. And x minus 2 to the power of n. Now we're ready to close absolute value bars and run through the computation. But whenever you use the ratio test, the algebra and steps almost always look about the same. We're expecting a lot of cancellations on the very next step. which will be now the limit as n goes to infinity of something. So first thing that happens is there's just no way that negative 1 to the power n plus 1, negative 1 to the power n can't survive due to the absolute value. So those factors are gone. Next, we can cancel x minus 2 to the power of n into x minus 2 to the power of n plus 1. And that leaves an x minus 2. But the absolute value bars are still affecting that portion. So we have to recall to put them in at that step. Next cancellation is the 2 to the n. So this 2 to the n cancels with this 2 to the n plus 1, leaving a 2 down below. And that's our limit. Any questions about the limit so far? This may be the most bizarre limit we've seen to date in this class, which makes that kind of exciting. What would you say the value of this limit should be? Not quite. It's a horrible, horrible trick question almost.
Well, there's no limit because there's no n.
There's no n, yeah. So this is effectively the limit of a constant, right? We're allowing x to vary, but when we use a ratio test, we imagine x is fixed. So x is not changing according to the limit where n varies. If there is no n, this is effectively the limit of a constant. And the limit of the constant is always that constant. And it's kind of similar to evaluating these kind of limits. If you do the limit as x goes to infinity of e to the negative x, this limit would be 0 because that function has a horizontal asymptote as we go off to negative infinity. But if you do the limit as x goes to infinity of just e, what would be the value of that limit? Just e. So we're really doing the same thing way down over there. It just looks much, much more abstract due to the variable x in absolute value and everything that's going on. But by our limit laws, this is in fact equal to x minus 2 in absolute value divided by 2. And we said this will converge whenever the limit is less than 1. So it would look like that. So x minus 2 divided by 2 less than 1 will now tell us we have convergence when absolute value of x minus 2 is less than 2. And at this stage, we have half of the objective already. We want to find the radius and interval of convergence. What would you say the radius should be at this stage? It's 2, correct. Keep in mind, we can make that determination only when we've taken care of any divisions or multiplications at this step, so absolute value is isolated, and there cannot be a coefficient to x inside the absolute value, or we'd have to find the interval of convergence first, then the radius. But I always double check both of them to see if they're consistent with each other. So we have x minus 2 is less than 2. This equation here can be converted to a triple-sided inequality, which reads negative 2 is less than x minus 2, which is less than positive 2. Then what we'd like to do is add 2 to all three sides of that inequality. We'll get 0 on the left is less than x, which is less than 4. So the ratio test tells us that we'll have convergence to the original power series, this one, specifically when x is between 0 and 4. What it doesn't tell us is what happens at 0 and 4, but we do know that if x is larger than 4, that's divergence, and if x is smaller than 0, that's divergence as well. So we're off to the next portion where we have to test the boundary points, 0 and 4. Any questions then before we test those boundary points? Okay, these are really, really long problems, and what I added to our very new assignment number 10 is if a problem looks like this, where we have to do the ratio test and then 2 more tests for each of the boundary points, that's going to be a 10-point question. squared, or exponent laws would say that's the same as negative 1 to the power 2n. But what happens to negative 1 to the power 2n? And let's see what that should definitely be equal to. It should be 1, correct. 2n is always an even integer no matter what. So pick any choice for n, double n is even, and a power that's even on negative 1 is always positive. So this is nothing but a 1. It's a very interesting series. That means this entire series when x is 0 becomes a summation as n goes from 0 to infinity of a 1. So would that converge or diverge? It's probably the most unusual series we've seen in class to date. Really special class, I think.
Is it under the conditions of a ratio test?
Typically in this case, let's see, for the ratio test, it can be used on any series whatsoever. And if we did try to use the ratio test, it's always this kind of limit, right? But a sub n plus 1 and a sub n are both 1, so this would turn into the limit as n goes to infinity of a n plus 1 divided by a sub n, which is the limit as n goes to infinity of 1 divided by 1, which is 1. So that comes out to a 1. What happens when the limit is 1, however?
The test failed.
The test fails. Yeah, that's horrible. Well, that's a really interesting question. And one thing that I was thinking about is usually when we test for or find the radius interval of convergence in a power series, we would use a ratio test. And from experience, it's highly unusual to see the ratio test used a second time. Not saying it could never happen, but usually we pick a different test. And this illustrates probably one of the reasons why. But so if this test didn't work, we need a different test. But first I'd want to ask, how do you folks feel about that? Does that look like it's convergent or divergent? Or what is even happening with n goes from 0 to infinity of 1 in summation?
It's just at 1 forever.
We're adding 1 forever. So this is essentially the same as 1 plus 1 plus 1 plus on forever. But for the series to converge, we have to be approaching a definite number. Are we approaching anything if we add 1 forever?
Infinity.
We're approaching infinity, right? So now we have a problem. We could say the series is actually equal to infinity. That's giving information on the particular way it diverged. But we still have to say it diverged, sadly. So we could either say it diverges because you cannot add infinitely many 1s and come up with a number, unless you have some strange math going on. So what you could do is just say, if you can expand this out and say it diverges because you're obviously getting an infinite amount, that would be okay. Or you could use this test. Let's take the limit as n goes to infinity of a sub n. That's the new a sub n after we evaluated x as 0. This is the same as the limit as n goes to infinity of the constant 1, but that's just 1, which is bigger than 0, so it does something by the test for, what was the actual test?
Test for divergence.
Yeah, we're using test for divergence. And the thing diverged then, because the test for divergence was successful. If we take the limit of the nth term, which is just 1, we get a value that's larger than 0, when in our case, we have divergence. But if you expanded the series and wrote it this way, and just said diverges, I think that'd be appropriate as well. Because that's, I think, pretty intuitive. It cannot be a number. Any questions so far? Okay, so we know the radius of convergence is 2. We know we converge whenever x is between 0 and 4, but now we know at 0 itself, we have divergence. So the interval of convergence now looks like this. A parenthesis because we diverged at 0. If it had been convergence, we would have put it in a bracket. So now we just do it again with x is equal to 4. Any questions to that step? Okay, let's do one more. Let's test when x is equal to 4. In this situation, the series as n goes from infinity, from 0 to infinity of a sub n, still this one, still the original problem, it now changes to the summation as n goes from 0 to infinity. We're plugging in 4, so it's negative 1 to the n, times 4 here gives us just a positive 2 to the n, divided by 2 to the n. This time we have an immediate cancellation, and it goes from 0 to infinity of -1 to power n. So how about that one? Is there any possibility that one can converge?
It would be 0, right? It would converge to 0 because if 1 minus 1 plus minus -1 plus 1.
Yeah, that's a really good point. If we were to evaluate this, we first put in 0, so it starts off as positive. We plug in 1, so the next term is -1. And we have 0 so far. But then we can't ever stop, right? So the next term is
Oh, yeah.
+1, -1, then +1, then -1.
So it does not exist.
It does not exist. The partial sums will bounce between 0 and +1 forever. That means the limit of the partial sums does not exist.
So it also diverges through tests for divergence.
Yeah, exactly. That's probably what I would do again. We can say the limit as n goes to infinity of -1 to the power of n flat out does not exist. And that is part of the test for divergence. In the test for divergence, if the limit of the nth term a sub n, which became -1 to the power of n when x was 4, does not exist, then you have divergence by that test. So I would say diverges by test for divergence. So that means at 4, we throw in a parenthesis as well. And that's the complete test. Now we know that that power series has meaning only if you're between 0 and 4, excluding the boundary points, 0 and 4. That's a heck of a review problem. But any questions so far about that kind of problem? Okay, so that's what we were getting into in section 11.8. And we mentioned towards the end of the class, what we would like to do is consider this as an actual function in its own right. In that case, this would have been the exact domain of that function. So the very next section is going to be a representation of particular functions using power series, where if we find the interval of convergence, we can say where that function's representation even makes sense. So that's what we're getting to next. Any questions before we give it a try? Okay, first let's start with building an important theorem. This theorem will go as follows. It says, let f of x be equal to the summation as n goes from 0 to infinity of x to the power of n. So that's our function that we'd like to represent as a power series, and which we just did. One thing we might ask then is, what is the original power series equal to? But we can say, by the geometric series test, we have that f of x is equal to the sum as n goes from 0 to infinity of x to the n is in fact 1 divided by 1 minus x, provided that the absolute value of x, which is the common ratio in the geometric series test, so x is playing the role of r, which has to be less than 1. So that's what the geometric series test provides for us. Drop the chalk. But any questions about that? I guess I would have a question about this. This feels kind of off in some sense. What exponent were we expecting right here when we do the geometric series test?
N minus 1.
We should have an n minus 1. So what we just did it with an n itself. That does require some explanation. So let's mention a little bit on what is going with that. So if we have something that looks like this, summation as n goes from 0 to infinity, let this just be r to the n. So we can think of an original geometric series test. We'd have a problem, we said, whenever we try to apply the geometric series test, because we expect an n minus 1. But also we were expecting a 1 here, correct? We will always start at 1, and we had an n minus 1 in the geometric series. But a new trick that we can apply is the following. So we want to re-index the series, which is always something that is allowable. what I would like to do is bring this back to something that we've seen before. So in my re-indexing of this series, I want to start at 1 rather than 0. So you can always pick your starting point on the series. That's kind of unusual, and it's something you can do, but you have to be very careful. Going here to here, I added 1. So when we go to Rn, r to the power of n, what would you say should be the new exponent if we added 1 to the index?
And -1.
We should subtract 1, correct. If we go -1, then we can compare both lists. They in fact produce the same exact terms like the one we were looking at on the first problem. So if we looked at this one right here, as n goes from 0 to infinity of r to the power of n, plugging in 0 we would get a 1, plus plug in 1 inside here we would get r, plus r squared when it's 2, r cubed when it's 3, and so on forever. If we look at this list up here, first we would plug in a 1 into r to the power n minus 1, but that would be the r to the power of 1 minus 1, and r to the power of 0 is still a 1. They'll go plus. When n is 2, we have r to the power 2 minus 1, that's just r. When n is 3, it'd be r squared, and so on. So we're really producing the same exact list, as long as we re-index in the corresponding way. If we added 1 there, we need to subtract 1 there. If we added 2, we would have to subtract 2, and so on. If we had a reason to re-index from here to -1, we would have added 1 to get an n plus 1. So that tells us the test there on the theorem, as n goes from 0 to infinity, is actually the right formula, because we can either let the index start at 1 and have the common ratio to the power of n minus 1, or start at 0 and have the common ratio power be just n itself, which is what we had exactly here. So this is really just the geometric series test repackaged in a new way. Any questions about it so far? Okay, so let's do our next bit. So that is our key theorem that's going to be used repeatedly throughout this entire section. But then another thing that we're going to do in this section is really the same similar kind of stuff as that we've used in this last problem. We're going to instead, this time, pick a function, try to find a power series representation of it, and then find its interval of convergence. So let's do all that next. But any questions first about the theorem? Okay, so let's go off to a new set of problems. And here our instructions say the following. Find a power series representation of the following functions. Then state the interval of convergence. I think that's about how I write this as an actual exam question. So if you see these kinds of instructions and you're given a function, let's say f of x is equal to 1 divided by, let's do say 4 plus x, then that will prime your brain to do the following steps that we're about to do. So what I'd like to do is be able to write f of x as some kind of power series. I may not be able to find its total sum. This was something that's very special using the geometric series test. But what we are going to try to do is use that theorem over there some way, somehow. If I can go this way, where this is the portion that is likely going to be different, then I'll have my power series. So we started with the function, we want this. That means I need to have a 1 in the numerator to start it off, so that's check. We need to have a 1 here, and that's our first problem. We need to eliminate that 4. So the algebra would look about like this to start it off. This is also equal to 1/4 times 1, which we like. We're factoring out 4 from the denominator, so this will be a 1, which is great, plus x divided by 4. So that's our first step. What's the next thing that we must have if we're trying to go right to left on that theorem?
Make x divided by 4 negative.
Yeah, we cannot have a positive sign here. we're going to force in a negative sign so we can go right to left on that theorem. So that's just like you said, we can call this 1/4 times 1 over 1 minus, then go minus x divided by 4. Then nothing has been broken algebraically. That's still the previous equality by canceling the negative signs. Now we're ready to say this is in fact equal to the summation as n goes from 0 to infinity. Gave it a little bit of room because there's also this 1/4. We just have to copy it in. But then we take this right here and we write negative x divided by 4 to the power of n. I should pause right there. Does that make sense on this very last step with the negative x to the power, negative x divided by 4 to power n? How do folks feel about that so far?
Honestly, I'm a little confused how you got there.
From here to here?
Yeah.
Yeah, that's really the kind of the key step. And sort of the logic behind that is no matter what I put inside here, it must carry to this step. So if I had for some reason in this theorem a 3x, maybe my favorite number is 3, so I stay the theorem that way, I would be forced to put a 3x here. So x is really playing the role of the variable. And in fact, it might be better to call it, say, an a to a, because that reminds us that the a can be anything, but the book doesn't state it that way. It's an okay way to view it, though. So if I use a instead, then whatever takes the role of a must go exactly there, provided that either x or a, let me bring it back to the way it was, is less than 1 in absolute value. Does that make sense so far to that step? Okay, so if we have 1 and a 1 here and a minus, anything that goes here, it must be copied into the series. So that's how we got to that step. Let's see here. Next thing we should do is possibly simplify that series as much as possible, because in some problems that becomes really, really important. So let's just take a couple steps right here to simplify down this series. So this is now equal to 1/4 summation as n goes from 0 to infinity. We can break this apart by raising all 3 factors to power n. So it'll be negative 1 to power n, x to the power of n, divided by 4 to the power of n. Then the 1/4 can multiply into the series and increase the power of 4 to the power n to 4 to the power n plus 1. So this is now the same as the summation as n goes from 0 to infinity of negative 1 to the power of n times x to the power of n divided by 4 to the power of n plus 1. So we've got it. That's our power series representation. The second portion of the problem is to state the interval of convergence. Any questions to this step so far? Okay, so as the namesake of the section says, we took the function 1 divided by 4 plus x, and we found a power series representation, which is summation from 0 to infinity of negative 1 power n, x to the power of n, divided by 4 to the power of n plus 1. But this does not hold for every single value of x. For example, I can't put negative 4 there because the left side is undefined, and very large values of x are also going to cause problems. So we can say this is the summary of our result going here all the way to here, and this equality will hold provided that the absolute value of something is less than 1. This is a departure from what we did in section 11.8. In section 11.8, the problem we just solved, we're given a power series and I want to find its interval convergence. I said we almost would always want to use the ratio test, but there are exceptions, and this is the exception. If what we have is truly a geometric series, and it is, at this step, that's a geometric series, then you do not have to use the ratio test. In fact, the ratio test would be a lot of extra work that you don't have to go through. So in this context, we are now using the geometric series test once again, and we're using this as our conclusion in order to get the interval of convergence. Does that make sense so far? That makes these problems actually really rapid, where the first initial attack to find the right form of 1 here, and a minus, that's really most of the work. So we can say that this all holds right here, provided that if I take this same quantity negative x divided by 4, it must be less than 1 in the absolute value. Okay, so let's work that out. This becomes positive x divided by 4 is less than 1. The absolute values will just wipe out the negative sign. 4 is positive, so it's unaffected, and it just consolidates around variable x itself. Then multiply both sides by 4, and we have the absolute value of x must be less than 4. So this equation holds, provided that that condition is met. And that tells us the interval of convergence, I, is now from negative 4 to positive 4, because that's the value of the triple-sided inequality, if we took one extra step. Any questions about that so far? There's still something unusual about this problem. When we did the previous problem, first problem of the day, we applied the ratio test. Then we had to go to the boundary points, say negative 4, positive 4 in this current problem. But we had to test for convergence / divergence for those two specific values. But this time, we're actually done. There is no need to test the boundary points whatsoever. It's guaranteed to diverge at negative 4 and positive 4. Anyone see what the difference is on why we had to do further work on the ratio test, but not this time? Let's take a look at those tests just to see kind of what's going on with them. So let's go up to the projector. Now first let's look at the ratio test. And that should be easily found on the Moodle site by going to Summary of Tests for Series. And the ratio test had this problem right here. Same with the root test. And this is the source of very long homework problems right here. If the limit comes out to 1 in the ratio test, then the test fails and we have no information on convergence or divergence at those points where the limit comes out exactly 1. That's really the reason we had to do further testing whenever we use the ratio test. But here we're really using the geometric series test. The geometric series test says convergence when you're less than 1 and divergence when you're equal to 1 or greater than 1. So it's taken that failure condition where the ratio is equal to 1 itself, and for the geometric series test, that's a guaranteed divergence. There's no further testing to make. So that's a wonderful, wonderful fact that you're welcome to take advantage of. I would highly, highly encourage it. And I mention all that because a typical thing that happens in the homework is people get to here, and then they test the two boundary points. But none of that work is actually necessary. You can just stop here. So let's add an extra note here. We can stop here, since the ratio test was not used. We use the geometric series test, which gives us the overall conclusion in just one shot. Really kind of cool. But any questions or comments at all about that sort of problem? Should we try one more kind of like it, just for the practice? Okay, let's go for another one. So same instructions as before. Same theorem as before. Really, this is our one big theorem in this section. And this time we're going to work with, once I get the right problems, let's hide that. That would work. Let's deal with, say, f of x is equal to 2x power 5 divided by 1 minus, let's make it, let's go with that. 1 minus 2x squared. It doesn't have to be completely crazy. So this is our new function. And we'd like to represent it through a power series. There's problems with this function, but all we need to do is we're going right to left on this algebraic form. So first thing is produce a 1 in the numerator. That is missing here. But you can just take 2 times x to the power 5, multiply it by 1 over 1 minus 2x squared. Then we're essentially ready to go at this stage. We have the 1 in the numerator, which we need to have. We start with the 1 as a leading term in the denominator. There's a minus. And the thing that goes here is going to be 2x squared. It's a good idea to associate it, to remind us that 2x squared was going to go here, here, and here, all in one shot. Any questions to that step so far? Okay, so now we can say that this is equal to 2x to the power 5 times the summation
as n goes from 0 to infinity of, we take whatever is here, 2x squared, and raise it to the power of n. And that's our power series representation for that function. Any questions at all so far? Okay, you can stop right here, but I think it is always a really, really good idea to simplify these things as much as feasibly possible. Because some of these problems down the line are going to require us to work further with this, and if it's not in its most simplified form, it could be quite a lot of work. So let's take some time to practice the algebra of simplifying these things. I would first always break down everything that's inside here using exponent laws for n. So we can start with 2x to the power 5. Chalk is not lasting today. Times the summation as n goes from 0 to infinity of 2 to the n times x to the power of, well really when we use exponent laws, n is multiplying, so it's to the power of 2n. And now we're ready to take another step to bring in the constant multiple, 2x to the power 5, all the way inside. So the next step is, this turns into the summation as n goes from 0 to infinity of 2 to the power of n plus 1, because with exponent laws, the powers will add. What should be the power of x then? Is it 10n or 2n plus 5? Or say 2n plus 10 for a ridiculous answer? Either A or B.
2n plus 5.
Exactly, yeah. So this exponent of 5 should add to the 2n. So we have a 2n plus 5. So that's the power series representation of f of x. What we could do then is, once again, you can test this by the ratio test, which is an awful lot of work. You'll get the same conclusion that we'll get with our shortcut, which starts right here. So all of this chain of equalities works provided that something in absolute value is less than 1. And that's this part of the theorem here, coming from the geometric series test. What is the actual x in our problem that has to be less than 1 in absolute value?
1 minus 2x squared, or just 2x squared?
Exactly. Whatever went here or whatever went here in this step. So 2x squared must be less than 1 in absolute value. So the absolute value here was redundant because 2x squared is non-negative no matter what. So we get 2x squared without absolute values is less than 1. Then the algebra gets more interesting still. Again, in these problems, we're not going for the radius of convergence, just the interval of convergence. And I need further steps to actually get that interval. The next step would be to divide by 2. So now x squared is less than 1/2. That doesn't tell me the interval of convergence is negative 1/2 to positive 1/2 until I get to a step that looks like this down here. So I need to do some extra algebra, and that's where a nice handy formula comes into play, which says that x squared, when we take the root, is truly nothing but the absolute value of x. So if we take the square root of both sides, we'll produce an absolute value. Does that make sense so far? Okay, then this algebra may feel different to some folks, so let me know how you feel about this. I had x squared is less than 1/2, and whenever we're dealing with equations or inequalities, if we take the square root of both sides, we have produced a problem involving positives or negatives. That's because of skips or step skipping. That step skipping was the absolute value portion. This is what's producing the positive or negatives when you take the root on both sides. So if we don't skip that step, this turns into the absolute value of x, which is less than the root of 1, which is 1, divided by the root of 2, which is the root of 2. There it is. So that's what we will get to on the very next step. Now if we want pluses or minuses, that would be going from the absolute value equation to the triple-sided inequality. Negative 1 over root 2 is now less than x, which is now less than positive 1 over the root of 2. But any questions to that step? Okay, well really that is the interval of convergence. It's just written in inequality form. If the interval of convergence is nicer to you as interval notation, then this is what it would look like. Negative 1 divided by root 2, and you could rationalize these if you would prefer, but I'm open to non-rationalized answers, so that's okay. So that's our interval of convergence. So the punchline to all of this work, probably half the chalkboard or so, is that this function, 2x to the power 5 divided by 1 minus 2x squared, is in fact equal to this as a power series, only when you pick x's specifically in that interval. For other values of x's, that power series would diverge. Any questions with that problem so far? So we have power series representations of functions really just using this. But you might notice our functions have been kind of boring so far. They've just been rational functions. So we can do it a little bit better in section 11.9, but to truly do really great, to get power series representations of sine, cosine, e to the x, tangent, logarithms, we have to do Taylor series and Maclaurin series. But there's some very, very specific situations where we can still do a little bit with some more exotic functions. So let's do that next. Unless there's any questions so far.
I got a
Yeah.
question. So what's the point of doing all that work? Because we know that the 2x squared is going to be the function that we compare it to 1, right?
Yeah.
So what was the point of doing all that work? Because if we already have that from the very beginning, like can't we just...
Oh, sorry.
I just don't see why we need to do all that work because
You
it...
mean doing all this work right here?
No, above.
Oh, all above.
Yeah.
Well, what we wanted to do with the first part of the instructions was find the power series representation.
Oh, okay.
And so that was this right here. So that provided essentially half of the answer to the overall question.
Oh, okay. Gotcha.
Other questions about that? Okay, let's try it again for a more exotic function then, to see how these things can go. So I have the same instructions, and if this were, say, an exam problem, I would probably add a little bit extra. So let's also add a little bit extra to these instructions. So I have a new function, and this time we want to find a power series representation, determine the interval of convergence, and we also want to find the power series representation by differentiating first. So there's a little bit extra to do this time. We want to differentiate the function first so we can find the power series representation, which implies we have to take an antiderivative at some point as well to get back to the original function f of x. So let's see how that goes. Let's try something with arctangent. So f of x is going to be tangent inverse, or arctangent if you prefer, of 3x. So the problem says, well, we want to find the power series representation of this problem, but notice that tangent inverse of 3x seems to have nothing at all to do with this as a function. So we're kind of stuck if we didn't use differentiation. But the problem is giving us a hint saying, if we did differentiate that, we could tie in the power series representation for the derivative using this theorem. So we'll start with that. If f of x is tangent inverse 3x, then let's go with f prime at x, which will be 1 divided by 1 plus, and input squared times the derivative, d dx, of whatever that input had to be. So the chain rule format of that derivative will look about like that. Then the input is then 3x, which goes in those two positions. And the parentheses are massively helpful because we have to have a 9x squared here. So the denominator is 1 plus 9x squared, and the derivative of 3x is just 3. So now we have a rational function. It was just a fluke that the derivative of the function we picked came out that way, which means the geometric series test is back on the table. We just have to put that in its proper format. Any questions so far? Okay, so there's two problems. The first problem is this has to be a 1, and the second problem is that this has to be a negative. So we can correct both of those in one shot by saying that this is equal to 3 times the fraction 1 over 1 minus something, and that something would be negative 9 x squared. So now we're ready to apply the theorem. The theorem is only applied to this portion right here, where the x and the x to the n and the absolute value of x is now going to be negative 9x squared, playing the role of the original x. Any questions so far then to that step? Okay, so let me take another step to say that this is then equal to 3 divided by, or hang on, 3 times the series as n goes from 0 to infinity of negative 9x squared. Let's go with green on that. To the power of n. So we've done it. We have a power series representation of the derivative. We want a power series representation of f of x, which still means we have some work to do, but we're getting there. Any questions at all to this step so far? Okay, the next thing we're going to need to do is we need the interval convergence of this. But also, since we have a lot of work to do on this one, we need to simplify this as much as feasibly possible. So we're going to next say that this is the same as summation as we go from 0 to infinity, 3 times 9 to the power of n. Let's go with maybe negative 1 to the power of n first. There's entirely 3 factors there. 9 to the power of n, and x to the power of 2n. And it's still helpful to bring in that 3, combine it with 9 to the power of n. So let's do that on the very next step. Well, let's work that out down below in the scratch region of the chalkboard, just to see how that would go by exponent laws. So if we have 3 times 9 to the power n, we can combine that as a single base by first factoring the 9. This will be 3 times 3 squared to the power of n. The 2 and the n have to, well, they have to multiply to give us 3 to the power of 2n. Does that make sense to that first step? Okay, so this 3 squared gave us the 9. This is now 3 times 3 to the power of 2n, but that's a 3 to the power of 1 times 3 to the power of 2n, so altogether, this is the 3 to the power of 2n plus 1. It's a good amount of work to do that, but that's really good practice, especially when you have a lot of stuff to do with the power series. So now this is becoming the summation as n goes from 0 to infinity of, we combined 3 to and 9, and we got 3 to the power of 2n plus 1, and x to the power of 2n. So now we're on our way. Again, we need the power series representation of f of x, and we need f of x's interval of convergence. So the next step might feel a bit weird. We have the representation for the derivative. We need to find the interval of convergence for the derivative at this step. Otherwise, we're going to do a lot of extra work if we get too far ahead of ourselves. So we can say that this equation holds, provided that. I mean, you don't have to say provided that, but it reminds me that we're using this condition over here. The absolute value of something is less than 1, and that something was the negative 9x squared divided by, well, just negative 9x squared. So we have to have negative 9x squared less than 1 in absolute value, which would mean 9x squared itself is less than 1. And we're really doing the same kind of steps as before. We can divide by 9 to obtain the new inequality that x squared is less than 1/9. Take the square root of both sides, and we've invoked an absolute value on the left-hand side. The square root of 1/9 is 1/3. And the triple side inequality is negative 1/3 is less than x, which is less than positive 1/3. So I have the interval of convergence for the derivative, f prime. That's a lot of work so far. Let's record that over here. So I is equal to negative 1/3, comma, positive 1/3. Now we're ready to go on to the next step. Any questions first before the very next step? Okay, so let me clear out this stuff. So for a problem like this, where in green it's telling you either to integrate or differentiate, we did the differentiation version first, there is a step 1, which would be all this work right here. Do the same thing as we did for the first 2 problems in this section for the derivative. For step 2, and there's only 2 steps, but they are very, very long steps, what we have to do is relate the derivative to the original function f. So let me write down something that goes like this. F of x is equal to the antiderivative of the derivative with respect to x. How do you folks feel about that as an equation? Does that seem okay so far? Really, this equation is saying that f should be equal to the antiderivative of the derivative, but yeah, that seems about right. The antiderivative of the derivative would be the original function plus a constant. So we do have one problem. There is infinitely many antiderivatives on the right-hand side. We need the one such that the constant of integration gives us exactly f of x. So that's something we have to address at the very, very last portion of this step too. But what we have is a formula for f prime and x as a power series. So this is now equal to the antiderivative of a bunch of stuff. I'll put it in brackets to say everything there is being affected by the antiderivative. And that stuff is all of this right here. So that, if you follow the long chain of equalities, gives us f prime is equal to summation as n goes from 0 to infinity of negative 1 to the power of n, 3 to the power of 2n plus 1, I think? Yeah, x to the power of 2n, close the bracket, and dx, since the antiderivative is with respect to x. So we're going to take the antiderivative of infinitely many terms in one shot. How do you folks feel about that? Does it even seem legit? It's actually a big problem in mathematics historically, where that's exactly what people did. If they had a power series and they needed to differentiate or integrate, then they just did it all in one shot with infinitely many terms, and it does not always work. But in certain conditions, and that's this humongous theorem, which we cannot copy the chalkboard because it takes way too long, under the right conditions, you can in fact integrate infinitely many terms. And that's this second part of the theorem here. If you have something along the lines of f of x is this as a power series, and you would like to integrate the thing, then the integral sign would be on the outside first, after we make the first substitution. But this humongous theorem says the integral sign can, in fact, commute inside the summation, which means we're integrating infinitely many terms. That is a really, really powerful theorem that the book will not try to prove. You have to take Math 3350 to see what the proofs of this kind of stuff will look like. So this was a huge open problem in mathematics hundreds of years ago, still modern mathematics, and people came up with amazing theorems in engineering and physics using this fact. And it's pretty recent that people were able to rigorously prove that this in fact works with the right conditions. And that's precisely the conditions that we're in. If we have a power series with a positive radius of convergence, our radius of convergence is 1/3, we can do this very next step. It's the same as the summation as n goes from 0 to infinity of the antiderivative of negative 1 to the power of n, 3 to the power of 2n plus 1, x to the power of 2n dx. So that's the use of that theorem above there. We can interchange or say commute the integral sign across a summation, even if it's a summation of infinitely many terms, provided our radius of convergence is positive. So now we're ready to do this antiderivative. I mean, it's the same as doing this one, but this feels less scary because this antiderivative is with respect to the variable x, and x only appears here. So all of this stuff is really just an overall constant with respect to this integration. So it turns into the summation as n goes from 0 to infinity of, so no change here, negative 1 to the power of n, no change here, 3 to the power of 2n plus 1. There is a change right here. What would be the antiderivative of x to the power 2n?
X to the 2n plus 1 over 2n plus 1.
Yeah, exactly. We go one higher on the power, so that's the plus 1, and we divide by that new power. But then, I have a question for you folks. There is still something missing in this antiderivative. To me, that's really subtle. Anyone see what's missing?
The constant.
We need a constant of integration, correct. It always torments us and follows us around. If we found an antiderivative, we were really finding infinitely many antiderivatives. So the next step of the problem is, we need this specific antiderivative such that this c gives us tangent inverse of 3x. So we need to now do this the next step. We can conclude, therefore, that seems like the right word if you've taken up most of the chalkboard with math. So therefore, tangent inverse of 3x is equal to the summation as n goes from 0 to infinity, negative 1 power n, 3 to the power 2n plus 1, x to the power 2n plus 1, divided by 2n plus 1, and this has interval of convergence, negative 1/3, positive 1/3. But do you believe that? I think that's kind of suspicious, right? I got this from going way, way over here, and this came from the geometric series test on the original derivative. I have interval convergence here. And another feature of this theorem says, if we integrate infinitely many terms, we will have the integral of f of x dx has the same radius and interval of convergence. And that's the same for differentiation. So if I already know what the interval and radius of convergence is, for this as a power series, I can differentiate it as much as I would like, and this will never change. We can also take the antiderivative of this as many times as we would like, and the interval of convergence is still always exactly the same. That's a tremendously important fact because, once again, you can use the ratio test on this. It does work. You will produce this, and if you test the endpoints, you will find it diverges on both of the endpoints. But that is doubling the length of the problem practically, and it's completely unnecessary. So find the interval convergence first, and then it carries down to the final end of the problem. Any questions with that so far? Oh, hang on, I didn't copy everything down. Plus C. The last loose end to tie up is we need to solve for C. Once we do that, we'll have the entire solution to this problem. Any questions then before we solve for C? Okay, so in order to solve for C, there's a specific trick that we like. This equation is meant to hold for every single value of x, provided you're between negative 1/3 and positive 1/3, excluding those end boundary points. So what is maybe the nicest x in this interval that you can input into this equation?
0.
0. 0 is always a great choice. We can say if x is equal to 0, then the equation becomes tangent inverse of 3 times 0 is equal to the summation as we go from 0 to infinity of, let's look at this carefully, we're putting 0 right here. So the whole thing is just 0. Would you all agree with that? So it's the summation as n goes from 0 to infinity of 0. I mean, we've seen this before with a 1, and that definitely diverges. But if you add infinitely many zeros, would you all agree that's a convergence? It had to converge because we're inside this interval. That's just a good thing to double check. Adding infinitely many zeros still results in 0, so we have convergence here, plus the constant. So now we have that tangent inverse at 0 is equal to 0 plus a constant due to the convergence to the total sum of 0, zilch. And we need to solve tangent inverse of 0. But if you review your trig, tangent inverse of 0 is 0 over 0, or excuse me, just 0 is equal to the constant. Because tangent of 0 would be sine of 0 divided by cosine of 0, and that would be a 0 divided by 1. So tangent inverse of 0 comes out as a 0, which means the constant is 0, which means if you forgot about the constant of integration, there would have been no harm done this one time. But I think that might be something that's important in the homework, so you may need to carefully see what C is equal to. But we just got lucky that the answer is tangent inverse of 3x is the summation as we go from 0 to infinity, negative 1 to the power of n, 3 to the power of 2n plus 1, x to the power of 2n plus 1, divided by 2n plus 1. It takes a lot of oxygen just to say, but we found a Fourier series representation of a function, and that was our end goal. Any questions about that problem? I feel like this is our first really, really long problem. It was solved in 2 phases, step 1 and step 2. I guess you could say step 3 is really solving for this constant. It is a really important step. So let's put it there as a reminder to ourselves. And then what I'd like to do is solve one more problem in this section, 11.9, where we repeat this, except we have to solve by finding the power series representation through integration, not differentiation. But there's no way we can do that in 1 minute. So we'll have to do that when we come back on Thursday. Then we'll also start 11.10, which is the capstone of the entirety of chapter 11. Any questions then before we call it a day, folks? Okay, if you do have questions, then feel free to stick around. I'll be happy to help.